Welcome, everyone. I'm excited to kick off today's presentation on understanding the roles of plasma, hemoglobin, and oxygen saturation in tissue oxygenation. This first slide sets the stage with our main focus on oxygen transport and delivery in blood. We'll explore how these components work together to ensure our tissues receive the oxygen they need to function properly. So, let's get started and dive into this fascinating topic. So let's explore where our blood actually carries oxygen. Primarily, oxygen is transported in two forms. The first is bound to hemoglobin, which is a protein inside red blood cells. This form is essential because it allows large amounts of oxygen to be carried efficiently throughout the body. When oxygen binds to hemoglobin, it enables our tissues to receive enough oxygen for their metabolic needs. The second form is oxygen dissolved directly in the blood plasma. Although only a small amount dissolves this way, it still plays a role in oxygen transport, especially in the lungs where oxygen first enters the blood. Understanding these two forms helps us see how blood ensures tissues get the oxygen they need, supporting overall body function. This process of oxygen transport and delivery is a key part of how our blood works as a whole. Let's talk about oxygen transport and delivery in blood. Although only a small fraction of oxygen is dissolved directly in plasma, this tiny amount plays a crucial role because it drives oxygen diffusion into tissues. Even though it's a small part, it's essential for understanding how oxygen moves from blood to cells. Now, when we look at the role of dissolved oxygen in tissues, one key point is the relationship between partial pressure of oxygen, or PO2, and the amount of oxygen dissolved. We can calculate this using a simple formula. PO2 multiplied by 0.003 gives us the amount of dissolved oxygen in milliliters per deciliter. This small coefficient means that as PO2 increases, the amount of oxygen dissolved also increases. In fact, doubling the PO2 doubles the amount of dissolved oxygen present in plasma. This linear relationship is important because it tells us that oxygen's solubility in plasma responds proportionally to changes in partial pressure. So, if PO2 goes up, dissolved oxygen goes up in a straight line, making this an easy relationship to understand and predict. Finally, to summarize how blood carries oxygen, apart from hemoglobin, which is the main carrier, some oxygen is simply dissolved in plasma. While this amount is small, it's vital because it provides the immediate source of oxygen that diffuses into tissues. This understanding ties into the overall picture of efficient oxygen delivery throughout the body. Let's talk about the importance of plasma PO2, which is the partial pressure of oxygen in the plasma. This value is really crucial because it directly affects how much oxygen binds to hemoglobin. The more oxygen there is in the plasma, the more efficiently it can be transported throughout the body. This concept is vital for understanding overall oxygen transport efficiency. It impacts not just how much oxygen is available, but also how effectively it moves from the lungs into the blood and from the blood into the tissues. When we look at the impact on hemoglobin binding, plasma PO2 influences the direction and rate of oxygen diffusion. In the lungs, a higher PO2 encourages oxygen to bind to hemoglobin, while in the tissues, a lower PO2 helps oxygen to release where it's needed most. Ultimately, plasma PO2 plays a key role in oxygenation, both of the blood and of the tissues. If the PO2 is too low, tissues may suffer from hypoxia, but if it's properly maintained, oxygen delivery remains efficient, supporting healthy tissue function. This concept ties back to the overall theme of how our body carefully regulates oxygen transport to sustain life. Oxygen transport and delivery in blood is a fascinating process, and at the heart of it is hemoglobin. Hemoglobin is absolutely essential for efficient oxygen delivery to the tissues. Without it, our blood wouldn't be able to meet the minimal oxygen needs of our tissues, which highlights just how critical hemoglobin is for survival. Now, when we talk about oxygen carrying capacity, hemoglobin plays a central role. It allows whole blood to carry about 20 milliliters of oxygen per deciliter at a normal arterial PO2 of 100 millimeters of mercury. This capacity is what keeps our tissues adequately supplied with oxygen under normal conditions. Most of the oxygen in our blood isn't just dissolved in the plasma, it's actually bound to hemoglobin. This binding is what makes oxygen transport so efficient. So when we ask, how does blood carry oxygen? The answer is primarily through this process of oxygen combining with hemoglobin. This interaction enables blood to transport large amounts of oxygen quickly and efficiently, ensuring our tissues get the oxygen they need to function properly. In essence, hemoglobin acts as a carrier, making oxygen transport in our blood both effective and reliable, and connecting directly to the overall theme of how our body sustains life through proper oxygen delivery. Now, let's take a closer look at oxygen transport and delivery in the blood. Tissues actually consume about 25% of the oxygen that the blood delivers, which highlights how vital efficient oxygen delivery is for our body's functions. When we talk about oxygen utilization efficiency, that 25% figure really stands out. It shows how much of the delivered oxygen is actually used by our tissues. At rest, the body needs roughly 250 milliliters of oxygen per minute to keep everything running smoothly. That means our blood is delivering about 1,000 milliliters of oxygen to the tissues every single minute. To put that into perspective, the heart pumps around 5 liters of blood each minute, which is quite a substantial flow, ensuring that oxygen reaches all parts of the body efficiently. So, in summary, oxygen delivery by the blood is a critical process, and understanding these numbers helps us appreciate how our cardiovascular system supports vital functions. It's all about how effectively blood can supply oxygen to meet the body's needs at rest and during activity. Let's take a closer look at how oxygen is transported and delivered in the blood, starting with the hemoglobin molecule. Now, hemoglobin is a large, complex protein that resides inside red blood cells, or erythrocytes. Its primary role is to carry oxygen from the lungs to tissues throughout the body. One important concept to understand is the difference between deoxyhemoglobin and oxyhemoglobin. Deoxyhemoglobin is simply hemoglobin that is not bound to oxygen. This form is crucial because it allows hemoglobin to pick up oxygen in the lungs and release it in the tissues. The structure of hemoglobin is specially designed to enable efficient oxygen transport and release. When hemoglobin binds oxygen, it forms oxyhemoglobin, which we denote as HbO2. Each hemoglobin molecule can bind up to 4 oxygen molecules, thanks to its 4 subunits. This high binding capacity makes hemoglobin incredibly effective at oxygen delivery. So, in summary, the structure of hemoglobin allows it to switch between deoxyhemoglobin and oxyhemoglobin states, effectively capturing oxygen in the lungs and releasing it where it's needed most. This dynamic process is fundamental to maintaining proper oxygen levels in the body and supporting overall cellular function. Let's talk about how oxygen exchange works efficiently in our blood. This process allows hemoglobin to pick up oxygen in the lungs and release it in the tissues seamlessly, one after another. It's a highly coordinated effort that ensures our tissues get the oxygen they need. Now, a key part of this is increased affinity. What that means is, when one oxygen molecule binds to hemoglobin, it actually makes it easier for the next oxygen to bind. This cooperative binding is crucial because it helps hemoglobin load oxygen quickly when oxygen levels are high, like in the lungs. The initial step is the binding of just one oxygen molecule. When this first oxygen attaches, it causes a change in the shape, or conformation, of hemoglobin. This shape change then makes it easier for additional oxygen molecules to bind, creating a positive feedback loop that enhances oxygen uptake. All of this ties into the broader theme of oxygen transport and delivery in blood. The cooperative binding of oxygen to hemoglobin is what makes our oxygen delivery so efficient and responsive to different needs in the body. It's a beautifully coordinated process that underpins our ability to sustain life. Let's talk about how oxygen is transported and delivered in the blood. The key term here is saturation, which tells us the percentage of hemoglobin molecules that are bound with oxygen. When we say oxygenated hemoglobin percentage, we're referring to how much hemoglobin is carrying oxygen at any given time. In normal venous blood, the saturation is about 75% when the partial pressure of oxygen, or PVO2, is around 40 mmHg. This means that even in venous blood, a significant portion of hemoglobin still carries oxygen, but it's less than what's seen in arterial blood. Now, in arterial blood, the oxygen saturation is typically about 97.5%, with a PaO2 of roughly 100 mmHg. This high saturation indicates that most hemoglobin molecules are fully loaded with oxygen, which is essential for efficient delivery to tissues. When we achieve 100% saturation, it means every hemoglobin molecule is bound with 4 oxygen molecules. That's the maximum capacity of hemoglobin to carry oxygen, and it's critical for ensuring tissues receive enough oxygen for their needs. Understanding these saturation levels helps us grasp how blood efficiently picks up oxygen in the lungs and delivers it throughout the body. It's a vital part of how oxygen transport maintains overall tissue health and function. Let's take a closer look at oxygen transport and delivery in blood. While saturation is a useful measurement, it alone doesn't give us the full picture of how well oxygen is being delivered to tissues. Saturation indicates how much hemoglobin is bound with oxygen, but it doesn't tell us about the total oxygen content in the blood. For example, conditions like anemia can reduce the amount of hemoglobin available, which means even if saturation levels appear normal, the actual oxygen content might still be low. This is a crucial point because it reminds us that a saturation of 100% doesn't necessarily mean the tissues are receiving enough oxygen. It's also important to understand that hemoglobin saturation percentage isn't a perfect measure of total blood oxygen content. Factors such as hemoglobin concentration and the actual amount of oxygen bound are key elements that influence oxygen delivery. So, in summary, while saturation provides valuable information, it's only part of the story. To truly assess oxygen delivery, we need to consider other factors like hemoglobin levels and overall oxygen content in the blood. Let's take a closer look at the oxygen transport and delivery in blood. The average arterial oxygen content, or CaO2, is about 20 milliliters per deciliter. This value represents the total amount of oxygen carried by the blood, and it's actually quite consistent within the normal range, which spans from 16 to 21 ml/dl. Now, an important point to understand is that oxygen is transported in 2 main ways: bound to hemoglobin and dissolved in plasma. The dissolved oxygen is a tiny fraction, and that's where the 0.003 factor comes into play. It tells us that for every millimeter of mercury of PO2, there are 0.003 milliliters of oxygen dissolved per deciliter of plasma. But most oxygen is carried by hemoglobin. Each gram of hemoglobin can carry about 1.34 milliliters of oxygen. That's a key number because it helps us calculate the total oxygen content based on hemoglobin concentration. When we look at the formula for CaO2, it combines these concepts: how much oxygen is bound to hemoglobin and how much is dissolved in plasma, giving us a complete picture of blood's oxygen-carrying capacity. Understanding this helps us grasp how efficiently oxygen is being transported to tissues, which is essential for overall metabolic function. Let's take a closer look at oxygen transport and delivery in the blood. On this slide, we see that the hemoglobin level is 9 grams per deciliter, which is slightly below normal, indicating some level of anemia or reduced hemoglobin. The arterial oxygen saturation, or SaO2, is 98%, meaning that most of the hemoglobin that is present is fully saturated with oxygen. The partial pressure of oxygen, PaO2, is 90 millimeters of mercury, which is within the normal range and suggests good oxygen availability in the blood. Now, moving on to the total oxygen content, or CaO2, this is a key concept because it tells us how much oxygen is actually being carried in the blood. In this example, the total oxygen content comes out to roughly 12.07 milliliters of oxygen per deciliter of blood. When calculating Ca-O2, we consider both the oxygen bound to hemoglobin and the oxygen dissolved in plasma. This example helps us see how these factors combine to determine the overall oxygen delivery capacity. It's important because understanding these values allows us to assess how effectively oxygen is being transported to tissues, which is vital for diagnosing and managing various clinical conditions. So, in summary, even with slightly reduced hemoglobin levels, a high SA-O2 and normal PaO2 can still support adequate oxygen delivery, but we need to consider the total content to get the full picture of oxygen transport in the blood. Now, let's look at the total oxygen content in the blood, which is calculated to be 17.52 milliliters of oxygen per deciliter. This value represents the total amount of oxygen carried by the blood, combining both hemoglobin-bound oxygen and dissolved oxygen. Next, the partial pressure of oxygen, or PaO2, is 72 millimeters of mercury. This measurement indicates the pressure exerted by oxygen in the arterial blood and gives us an idea of how much oxygen is available for diffusion into the tissues. Moving on, the arterial oxygen saturation, or SA-O2, is 92%, or 0.92. This tells us that 92% of the hemoglobin binding sites are occupied by oxygen, which is a healthy level but slightly below full saturation. Finally, the hemoglobin level used in our calculation is 14 grams per deciliter. Hemoglobin concentration plays a crucial role because it determines how much oxygen can be transported overall. Putting it all together, these values help us understand how oxygen is transported and delivered through the blood, reinforcing the importance of each component, partial pressure, saturation, and hemoglobin level, in maintaining effective oxygenation of the tissues.